one thing and adjusting the coefficient in front of it, and I think there were quite a few errors in my last lecture. So, I am going to do it again and fix all the errors. So, what we did was to choose a winding number 1, and so that was chosen to be divided by R. Probably I put sigma a by 2, that was one of the errors which was pointed out by somebody right after class. So, but anyway, so this is the definition of R, and so the idea was to define n, the winding number, to be some constant times integral over the 3 sphere some bunch of coordinates thetas. I gave you an explicit representation of that last time, and times trace of so here I will not keep putting this superscript 1 to remind it's this is going to be in general, this would be what we would take G d j G inverse and this is the constant we want to fix, and we will fix this constant by plugging in G1 and choosing the C such that you get n equal to 1. Okay, I am not proving that this is a topological invariant etc., but that is not very hard to prove. Okay, and so we are just going to do this computation, and so we needed to compute what G di G inverse should be equal to. This is what we wanted to compute, but without any computation I was able to tell you that this had to be of this form. This is you can see that if I just take a di is like some translation operator. So, it is just is asking how G differs when you move a little bit on the group manifold. So, this is just like a Lie algebra valued element. So, this has to be expanded in terms of the Lie algebra valued stuff. So, so it should be writable in terms of something like this. Okay, and so it came down to computing this u of a, and then we can plug things into this and we can get will get the answer. And so now so the thing is that we will use a nice trick out here to compute this, okay, basically to compute this number, and let us see how that goes. So what you do is let us think of the analog of the north. So we are on a 3 sphere and we pick any point on it is fine, but we will just choose what we will call the north pole. Okay, so the north pole will be this point tau equal to r and all the xa's being 0. Okay, it will be hard for you to imagine this thing, so it is better to think of the thing in right hand side. The reason I am calling it the north pole is because if you think of this the north pole in a 2 sphere would be precisely, you would have said z equal to the radius of the sphere and x and y coordinates being 0. Okay, this is just one higher dimensional thing. So, this a is 3 coordinates being 0, one of them being non-zero. Okay. So, I am going to choose this thing, and we want to choose what the idea here is that we can coordinates near the north pole are very easy. I do not need to use those coordinates which valid everywhere. So, nice coordinates so in a first order neighborhood, because in some sense we only want things in up to first order, okay, out here, and in computing taking a derivative, and then so nice coordinates are actually y a's or y a's, which I will just define to be x a upon r, okay, near the north pole. Okay. So the measure would, for instance, would be 9 will be just d cubed y, the volume measure on S3 for instance. Okay. So now the thing is we want to evaluate, so these i's are supposed to be coordinates on the sphere. So now what I will do here is di, so what I will do instead of evaluating any, I will just evaluate d of yi. So I will just choose this as my coordinate. So di, I will just say that this can be represented by d of yi. Okay. And so we just go ahead, now we can look at this and you see that g1 in this coordinate system would be tau by r, but tau by r in this tau is, where have I given, it is here. So you can see that tau by r will be equal to 1 plus order y square in the near the north pole. Is this clear? Okay. So what I am going to do is I am going to evaluate g di g inverse at the north pole, that is what I am going to do. Okay. So for that thing you can see that when I look I am looking for derivatives acting on tau, it could act on a term which is y square, but I am going to at the north pole y square, if you take a derivative of it will give y some you will get a y which vanishes. So I do not need to, so it is really very simple. All I need to do is to just take a derivative of the y's out here. So you can see that di of g1 is just I y a, this is x a by r, is just I sigma a at the north pole. Okay. And what about, so we have to, but we want to get g inverse, so it is not again hard to see that the inverse of that will give a minus, will come with a minus sign. Okay. Similarly, okay. So it tells you that UIA is really very simple, it is just one, it is a Kronecker delta. So this implies, in fact now you may ask what about G1 at the north pole is again, what is it equal to, y's are 0 and it is just identity matrix. At the north pole. Okay. And we had done this calculation yesterday, putting this thing in here, and we found that we were getting determinant of u. Okay. And what does that tell you? That the determinant of u is equal to 1. Okay. That is really the relevant thing. Okay. And so there will be no coordinate dependence coming on this thing. So this whole computation which you need to do just corresponds to doing some number coming from here times the integral over the sphere. I have not written out the exact measure, but that we know what the measure is, and we had worked out the volume of the 3 sphere last time. What was the answer? It was 2 pi square. So what we see that n1 should be equal to c times volume of S3, okay, times this trace of, there will be a minus I, so let me pull out the I cubed, epsilon I j k that is all that remains, right. Okay. And I had done some this computation last time, but I think there was some errors in what I had done. So, I will just repeat it, it will just take me a minute. So, the thing is, first thing I did yesterday was to convert this into a commutator, and there I think I messed up on a factor of 2, and this is what I should have remembered, that it is half sigma I which satisfies the SU2 Lie algebra, and we know the structure constant for that. So, that is I epsilon I j L half sigma L. Okay. So, now I can just so I want the sigma I sigma j commutator. So, this implies that sigma I sigma j commutator is 2 I epsilon I j L. Okay. So, the way the trick the way to do this is take sigma I sigma j, because there is an epsilon out here, I can write this as half of the commutator of sigma I sigma j, and that half will cancel this. Okay. So, now I can just do this. So, 1 equal to C times volume of S3, okay, times, then you get an I out of here from this. So, it is minus this thing into I times trace okay, and this is equal to 2 delta L k. Okay. So, you get 2, and then you get epsilon I j k if you contract with the delta L k, but that is 3 factorial, which is 6, and then you get a 2 from here, and then this this gives you minus 1. But we have already seen that the volume of S3 is 2 pi square. So, I can just write that out here. So, we get C equal to minus 1 by 12 into 2, 24 pi square. All this hard work was just to compute this, and this we have done only for SU2, but just to show you how it goes. Okay. So, this is just minus 1 by okay. So, this is how this winding number is this thing. So, now there are some exercises which you should do. Exercise is the following: additivity of winding number, which intuitively is clear. Suppose there are suppose G1 and G2 have winding number. I will keep calling it winding number, you understand what I mean, N1 N2 respectively. Then G1 dot G2 and G2 dot G1 have winding number, okay. So, it kind of more or less should follow from this definition. You have to plug and separate out things and see how it looks. Okay. So, that is the claim of the additivity of this thing. Okay. For instance, it is easy to see that G inverse has opposite winding number, because if you just look at that, that is a standard formula. So, if you replace G by G inverse, you will get G inverse di G inverse, but that is the identity which says it is minus of that thing, but each of them will change sign. Last check, minus 1 cubed, this was minus 1. So, it flips the thing, that is one. Okay. So, this thing, but now we would like to connect this up with yet another quantity which we will see, and so what I will show is that n has another expression, okay, and that is this is something which you have seen in your assignment. Okay. In your assignment you had found this quantity, you had shown that this quantity was a total derivative. Okay. So, all these formulae I am writing out, the numbers are correct only for SU2. Okay. So, what we showed was trace rather epsilon mu nu rho sigma f mu nu f rho sigma was writable as some d mu of, I think the symbol I used in the assignment was omega mu, and you were asked to find out what this omega mu was. And the answer is kind of nice. Mu nu rho sigma trace f nu rho a sigma minus 2/3 okay, and you can also write it if you substitute for what f is and you do things, you will find that that corresponds to flipping this sign. So, that is another formula you would see which would have d nu a rho a sigma minus plus 2/3 of this thing. And the easy way to check this is to just write, I mean in terms of derivatives etc., you look at this term, this has precisely 2 derivatives and you are pulling out one derivative. So, omega mu should be constructible from just one derivative and gauge fields. Okay. So, this is the term which has one derivative and 2 gauge fields, and this has 3 gauge fields. Okay, yes. So, there will be an I depending on, I think, Euclidean Minkowski, I am not okay. Huh? Which one? Yeah, okay. So you want to put, so in your assignment you got an I, okay, good. Okay, so right now I will I mean this is, these numbers are important, but what is more important is the structure out here, which is that it takes this form, it has this this thing, and so now because it is a total derivative, this thing, this is an integral over all space, this reduces to an integral. So, what that tells you is that integral of that quantity. So, I will just write it as epsilon ff, just to, since epsilon ff over 4 space will be equal to an integral over the 3 sphere at infinity times omega in the radial direction. Okay, this is what you should get, and so if you pick this thing to be the radial direction, this nu rho sigma will necessarily become along the space, along the S3. Okay. So, epsilon r mu nu rho sigma is should be identified with so these things should just take values which would be I j k. Okay. So, what I am trying to show you is that it is coming down to this. So, but omega r is a function of these a's, and but the key point here is we are choosing boundary conditions where the gauge field is pure gauge. Okay. So, now a priori it looks like these two are different terms, but for pure gauge they will give the same things and it will only change some coefficients, and that is what I have put out there. Okay. So, you can see that it is easy to see that this gives this term, this kind of term, but again here if you look at this f also will give the same term, it cannot give something else. Okay, because there is an antisymmetric guy working. So, so what I am saying is when it is pure gauge it comes back to this form. Okay. So, you can see that this object can be written in terms of complete 4 derivative of this kind, and I am just writing out the correct answer. Okay. and since we are so the other difference between what we did earlier and now is that we are in Euclidean space. We will see why we need to be in Euclidean space a little bit better, again we will see it later, but so now hopefully at least you can see that there are two different expressions, but they will match. Okay, so that was the reason for me to work this in some detail, okay, but I have not shown you that this coefficient becomes 16 pi square, that is for you to do. Okay. So that is just some sitting there and putting out looking at the various terms and seeing how they work out. So the question is now what we would like to do is to ask, can we find the general solution to, so what we want to do is to look for solutions Euler-Lagrange equations of motion such that a mu limit r tends to infinity of a mu goes to pure gauge. So I am just choosing for concreteness the winding number 1 example. Okay, so this is what we want to do, and you just go ahead and put an ansatz for, choose an ansatz for okay, and the ansatz is kind of nice, some function of r times and limit r tends to infinity f of r should be 1. Okay, and you can go ahead and solve the Euler-Lagrange. So you will get a nice differential equation for f of r, and I would recommend working it out, and so the answer turns out to be something like this, where rho is some parameter. Rho is a parameter which we will say is the size. Okay, you can see that this is a first thing is this is a length scale, rho is a length scale, and the reason to call it a size, it roughly gives you an estimate of how broad this thing is, because when r is less than rho, you can see, or much less than rho, this thing will be close to 0, and that is where it is deviating from the asymptotic this thing. So that naturally the size of this thing. Okay, the question to ask is what happens if you consider various symmetries that you have in the theory. Okay, so you have, what are the symmetries? So we have Poincare, but classically the Yang-Mills has a extra symmetry which is scaling and conformal. We have already seen some of that. So there is also scaling, and also there is what is called special conformal. So now the question is, so if you are given any solution to, so here let us assume that we have checked this is a solution to our equations of motion, and now we want to ask, well, how do these symmetries act on this thing. Okay, some symmetries will act trivially, but now we are in a gauge theory. So if for instance suppose I ask what happens under rotations, or or special conformal, you can it is not if your transformation is such that it takes a mu to a gauge transform of it, you would still say that it is the same solution, you will not say it is a different solution. Okay, so it is really this is the only subtlety or difference between when we looked at scalar things, we looked in gory detail. Here this is always modulo gauge transformations. Okay, so what you will find here is that the the following symmetries are broken. One is scaling, it is very obvious, if I scale everything rho changes, okay. So scaling is broken. Also translation in space time, these two are broken, all other things are not, okay. So for instance, hard exercise would be to actually take the special conformal transformation, put that into the solution and show that it is a gauge, it is not it is a gauge transform of what you have started out with, okay. That can be done, but I am not going to do it. So I am just saying that that is what is happening. So again here r equal to 0, there is nothing special, you can shift origins. So in some sense this is an object which is localized in space and time at some point, in this way here it is the origin, but there is nothing special about that point, I can always move it, okay. So you can so it is easy to shift I mean write solutions where it is shifted. So this thing has only 4 free parameters, if you will, 5 parameters free parameters. One is 4 from coming from translations in space and time and 1 from scaling, okay. So that is all there is about the solution, but the nice thing about this is that we need not solve these equations, we can solve a set of first order equations, they are much easier to solve, and that is what I am going to do. So it is very similar to what we did earlier, except now what we are looking at is finite action, we are looking at a situation of finite action, and so let us we had worked out the normalization with the traces. What is the normalization? Can you look up your notes and tell me? Was it 1/4, half, or half? Just last lecture we had worked it out, I think. Plus 1/2, is it? Okay. So the point here is that we can define the dual of f. This is just a generalization of what we saw in electric in the case of electromagnetism, where we saw that there is a symmetry which exchanges electric and magnetic field, okay. So the same thing we could do in general out here, and so just we define star f mu nu, or sometimes this is also called just f tilde mu nu. I keep switching back and forth, okay. So this is nice for people who are comfortable with the form notation, and so this is just defined to be half epsilon mu nu rho sigma f rho sigma. This is definition, okay. And you can see easily that if I take for instance electric field would be f 0 I component, and because of this that will go to I j of the other way, okay. And there is a difference, one difference, important difference between in Minkowski space if we define epsilon 0 1 2 3 to be plus 1, the lower guy would be minus 1. If then why is that? Because I have to lower these things, and irrespective of your convention, either 3 you have 3 minus signs or 1 minus sign. So this happens in all so in Minkowski space. So now you can say what will happen if I do this twice, okay. So in Minkowski space, basically because of this thing, if you do the star operation twice, so you would have thought, okay, I take electric field to magnetic field, and then I do it once more, magnetic field comes back to electric field, but if you remember there was a minus sign, there was an important minus sign. So what it does, if you do it 2 times, it does not go exactly to itself, it goes to minus itself. Okay. And you can trace the origin to this if you wish. Yeah. So, but you can see that if you are working in a strange space time where there were 2 positive and 2 negative of signature 2 2, this sign would not have appeared, or 4 0 also Euclidean. Okay. So, since we are going to be we are working in Euclidean space, we will not have this minus sign. Okay. So, in Euclidean space there is a big difference. In Euclidean space, okay. And so let us now do something in Euclidean space. Let us consider the following object, plus or minus square. Okay. So, if I expand this, by this I mean writing the other one with one upper etc. So, you can see that then I get this is equal to f mu nu okay, and then plus or minus 2 plus okay. But there is an important point here. If you look at f tilde, this is actually the same as this. Think about what happened, that this quantity was e square minus b square in Minkowski, but it became anyway it became e square plus b square. So, you can see that exchanging e and b, even minus sign and all, it does not matter which, these two will give you the same thing. Okay. So, I can rewrite this as 2 okay. But this object is positive definite. Okay. So, so what we can see is that integral of 1/4 of d4x trace of must be greater than or equal to 0, not a deep statement. Okay. But now we can use this, and so this implies that half, I am taking care of this 2 half integral d4x trace f mu nu plus or minus half okay. And let us look at this quantity. This is exactly the winding number guy, because what is this? So, let us work that out. Trace f mu nu f tilde mu nu equal to, there is a half in the definition, epsilon mu nu rho sigma okay. And so, the integral of this d4x is equal to okay. And what is this equal to? It's equal to yeah. So, integral of that thing is equal to minus 16. So, and there is a half here. So, this becomes minus 8 pi square n. It goes to 32. Wait, so what did we show? We showed that the integral 1 by 16 pi square ff epsilon ff was equal, minus of that was equal to n. So integral epsilon ff by 2, how? So this is equal to integral epsilon ff equal to minus 16 pi square n, okay. Half of that is 8. Okay. Is that clear? Is that okay? So then I have to, so what you can see is that this thing is now minus of 8 pi square n. So now we can see something nice happening. What we see is that, and this quantity is our action, so this is S Euclidean. So what we get is S Euclidean plus or minus or plus, or I will take it to the other side, is greater than or equal to 4 pi square n. Because there is a half, further half out there, okay. Hopefully there are no, I mean, so at least it is self consistent. I am not saying this is the correct answer or whatever, assuming my 16 pi square was correct, okay. But the point here is not that. The point here is that you can see that it is bounded, the Euclidean action is bounded from below, okay. So you can rewrite this as so this implies that it is strictly, we can replace it by mod n, okay. So depending on your convention, n equal to plus 1 is called an instanton, positive is called instanton, and n less than 0 is called an anti-instanton. Okay. And now you can ask, when is the thing saturated, right? Okay. So the equality is obtained when this quantity is 0, and now so when n is positive we choose the upper sign according to this, okay. So now okay, so when n is greater than 0, yeah, when n is greater than 0 we this will imply f mu nu equal plus f tilde mu nu equal to 0, and n less than 0 so these are first order equations, okay. So here this thing is when f equal to f dual, so this is called self dual instanton, and this will be called anti self dual. Okay. So these equations are a lot easier to solve because they are first order, okay. So in fact you can check if the binding number 1 solution that we wrote solves this equation, you should check that. So you go compute this thing and check if it satisfies that. So it is a lot easier because it tells you that all you need to do is go, you are given the ansatz for mu, you plug the thing in, you get a differential equation for f and check if that f satisfies, it is a lot easier. I just have a sort of a remark to make. If you remember when we did representation theory of the Lorentz group, we saw there were 2 SU2s, and we saw that any object would be specified by, which transform in a nice representation of the Lorentz group, would be given by 2 numbers, J1 and J2, and so for instance we saw that half half was the vector, okay. And but I told you that the field strength has is actually reducible, okay, and so it is an antisymmetry, so that actually comes like this, Okay. So, f mu nu has 6 components. So, this object will this is spin 1 which has 3 components, this has the. So, coming back to this thing, this setup here is actually these conditions correspond to setting one of these combinations to 0, and this is a Lorentz invariant condition. Okay. So, depending on your convention you can call this self dual part and this is the anti self dual part. So, if you give me a field strength which is neither self dual or this thing, you can just take linear combinations. Okay. And so, the way to do that is exactly what we saw here. So, you f mu nu plus or minus f tilde mu nu will give you the self dual and the anti self dual parts, and just to you can do this even in Minkowski, except you have to put an I, okay, because star square was minus 1. So, its eigenvalues are plus or minus I. Okay. So, this I would be there in this thing. So, these are the self dual and anti self dual parts of any antisymmetric second rank tensor. Okay. Are there any questions with? So, these equations are actually very very important and very nice. One of the things which one can show is that for instance, let us look at the monopole equation which we the Bogomolny equation which we saw, which we got by. So, in some sense the self dual Yang so these are, so if you are looking at configurations like this, we would call them self dual Yang-Mills configurations. Okay. So, in some sense these self dual and anti self dual solutions in a sense generate all solutions that we have seen in this course. Via dimensional reduction. So, I will just illustrate what I mean by this. What by that I mean whenever we the squaring trick worked, we got some we always had some equation which was first order. Okay. So, I will show you for instance how we can get the monopole equation. So, the idea of dimensional reduction is, so we are starting in 4 dimensions Euclidean, mind you. So, we are going from 4 to 3. Okay. And so I just take a, so we chose our 4 to be 0, 1, 2 and 3, and we will just say that we will look for configurations. Usually what people do is when they Wick rotate they call 0 as 4, but I just did not do that, it does not matter. Okay. So, I just say that things are, we have already seen this idea, we say that things are independent of this coordinate. Okay. And so, this A, so A0 behaves like what? Like an adjoint scalar Okay. So, let us look at the self duality equations and just look at the thing is pick say let us say that let us choose this and say mu is 0. Okay. So, we have to look at f. So, this will also we saw that f 0 I. So, we will use I for these 3, f 0 I will just become the covariant derivative of this is something which we have already seen, and f I j nothing will happen because so and we so what that tells you is that f 0 I for self dual equations f 0 I is equal to f tilde 0 I, which is equal to half. So, let us take f 0 1 just to be concrete, others will just follow. What we will get is half of epsilon 0 1 2 3. So, this will be just half of, no, half will go away, this just will become F23. Okay. But what is F01? It is this thing. So, this equation just becomes, so this just becomes F23 plus plus or minus, yeah, minus D0I, sorry, D1 of A0, which we will call, what did I write here? I wrote something completely di of, so we will just call this, we will call it a scalar phi. So, it just becomes di of phi, terribly sorry. So, that just becomes d1 of phi equal to 0. Okay. So, this would be the B field, the analog of the B. So, this is the equation, if you remember, which in the Bogomolny limit, this is exactly what we got. Okay. Now, it gets more interesting. You can ask, for instance, what happens if I take go one further dimension below. Let us say that look at 0 and 3, keep 1 and 2 and make things independent of 0 and 3. Okay. So, now there will be many pieces. So, what this tells you is that suppose you are able to write if you are able to solve these equations, you can in fact guess some solutions of this kind also. You could write different things, you can solve these things. In the context of monopoles, this was this is due to norm. So, these are sometimes called Nonz equations. Okay. And if you let us go now from 4 to 2, so things are independent of 0 and 1 coordinate, and what I will 0 and 3. Okay, and just let us just call these two scalars as phi 1 and phi 2. So, I end up with two adjoint scalars, and I need to work out what. So, I runs only from 1 and 2. So, you have F0I, which will go to F0I and F1I. This will just go to D0 di of phi 1 and di of phi 2. Okay. And Fij will remain F12, there is nothing. So, but there is now the other bit which we saw already, F03 will go to the commutator of phi 1 and phi 2. I am very loose here with signs, signs are not so important, I mean the structure is much more important. Okay. So, now let us look at this equation and choose F12 out here, for instance. So, choose the same equation, I choose F12. So, I get F12 equal to tilde F12, which will become the same as F03. So, up to a sign again 1 2 wait. So, we started out 0 1 2 3. Okay. So, F tilde 1 2 will be F30. Okay. So, minus, just call it okay. And but there is still one more equation I could have considered. I could have considered F0I here, then I will get the other guy. So, what we will get is something like this, F01, which would become di of phi 1 will become equal. So, di of phi 1 will become will get the other guy, right, F. So, this will just become minus some epsilon, again sign I am little bit loose with the sign, epsilon ij of dj of phi 2 equal to 0. This equation looks a little bit messy, but it will become very simple in a short while. Okay. So, let us just do so since we are in 2 dimensions. So, these are called the vortex equations, these are the non-abelian vortex equations. They are also called Higgs equations. Okay. So this I will write it in a nicer way. This epsilon ijk makes it look a little bit weird, but actually suppose we went ahead and defined a complex phi. So these were real scalars. So I can complexify it, I can define phi to be phi 1 plus I phi 2. And we are in 2-dimensional space time. I can take the coordinates and work with we can just define z to be x plus iy. Okay. Then this equation takes a nice form. It becomes up to again factors something like this. Okay, so this is like a gauged version of the of a Cauchy-Riemann condition. Okay, so this says that so this has nice meaning, but this is written in a sort of compact form. This is what you would get. Okay, but of course you can ask what happens, what is the difference between anti self dual and anti self dual. One would correspond to holomorphic, that means it is a dz bar, the other one will correspond to dz of phi being 0. Okay, so that is what will happen. Okay. So there is a sense in which the self dual system is special, and everything else comes from that. Okay. And so the thing is, now the question is, can we find all the solutions to, so if you give me winding number n, you can ask can you give me a solution first, okay, of that equation. Second bit is, can you get all the modes, like I explained here. The instanton carried 5 numbers, one was the scale and the other one was the translation modes. Suppose we have we saw one more nice thing, we saw that we could get let us say we have instanton number 1 solutions here, one localized here, one localized here of this size. Okay. This guy has 5 parameters, this guy also has 5 parameters, but actually there is a relative SU2 also. So that will give you another 3 parameters plus some parameter, I think it is 3. Okay, let us just keep unless there is a further U1 or whatever. So what that tells you is that if you are looking for something which has instanton number 2, that will have many more parameters than just those. So far away when you take, so there will so there is also, yeah, so the point here is that as you there will be a solution where these come closer, and then there will be a full proper winding number 2 solution. So the question is, how do you go about writing these solutions, and depending on how much time remains in this course, we will discuss the ADHM construction, but I just want to point out that there is this construction due to these guys, and there is a beautiful understanding which came much later in the context of string theory, where we actually understand where these equations came from. Okay, so what they do is to solve some auxiliary linear equation in some this thing, and they show that the consistency condition for those set of equations is the self dual Yang-Mills. Okay. What 't Hooft had done was he wrote for instance a 2 instanton solution explicitly, but it did not have all the parameters. Okay, and you know that there has to be a solution, just based on symmetry arguments there must be a solution which has this many parameters. Okay, in my counting it is 13, but I am not sure about that. Okay, I am just doing it at the top of my head. There might be a reduction which might come, and so these 4 authors there. So for once I will give their names: Michael Atiyah, Drinfeld, Hitchin, and Manin. So 2 Russian and 2 English or British authors. They gave this miraculous construction which had all the parameters, and their solution will work for any group, any non-abelian group. It is not just SU2. Okay, so it is really, I mean, it is amazing. In I think 2 pages or 1.5 pages of physics letters B, this was completed, and it took us many. So this was, I do not remember when, but I think the first nice understanding which I have seen for this is due to Douglas, which came around 96 I think, in a paper I think titled brains within brains or whatever, and it explains sort of a dual perspective, and this is something we will discuss dualities at that time, maybe time permitting I will discuss that.